have to be stored in the memory. Alright? So, and you have to repeatedly call one function, the other function, the same function, calling it several times, and then solve it back. So, as a programming project, you could try to implement such things, not this, but another kind of problem using recursion, and you will see that it's far more time consuming compared to the simple for loop with the iteration where you multiply 1 times, 2 times, 3 up to 5 or whatever number. So recursion is not always the best solution, but it may be sometimes the only way you can solve a problem. But if you can solve a problem through iteration, it is far more easier normally. Okay? Both will involve the same number of multiplications. We'll do the analysis now. But because of the architecture overhead, you have to store everything in the memory and then call things back and forth. It will take time. Okay? Alright. So now let's do the analysis of it. So what can I say? To find factorial of n, I have to find f of n is f of n minus 1 times n. So in terms of the basic operation, what do you think is the basic operation here? Huh? Multiplication, right? To find f of n, I need to find f of n minus 1 and do a multiplication with n. So each step, I'm doing one multiplication, each recursion call actually, I'm doing one multiplication. So it means, if I want to find the number of multiplications I need to do to find n factorial. So m of n means what? The number of multiplications to find n factorial. Okay? That's what it means. So m of n means number of multiplications to find n factorial. So if I want to find n factorial, f of n, how many multiplications I do? That's indicated by m of n. So m of n, based on this recursive equation, right? You shall see recursive recurrence relation, that's what we call it. Have you heard of this terminology? This is called the recurrence relation. So we can say f of n is f of n minus 1 times n, and recurrence relations normally have a basic condition like we have one here. So here the basic condition is f of 0 is 1 because the recurrence has to stop somewhere. Okay, so f of 0 is 1. So you always write them together like I state here. This is the recurrence relation. Okay, so f of 0 is 1, so then this recurrence basically holds good for any n greater than or equal to 1. Like f of 1 is, as I wrote, f of 1 is f of 0 times 1, f of 2 is f of 1 times 2 and so on. So for any n greater than or equal to 1, the first recurrence holds good. And if n is 0, f of 0 is 1. That's what it means. Okay? So now let's go and analyze the time complexity in terms of the number of multiplications. So how many multiplications you are going to find n factorial? Okay? So if you see the recurrence, this recurrence over here, to find n factorial, I need to know n minus 1 factorial, right? So whatever the number of multiplications I would encounter to find n minus 1 factorial, right, that many number of multiplications, then how many more multiplications I have to do to find n factorial? Whatever the number of multiplications, I don't know that for the time being. So whatever the multiplications I have to do to find n minus 1 factorial, that plus one more multiplication is needed to find n factorial. So whatever is needed for n minus 1 factorial plus one more multiplication, this multiplication is needed to find n factorial. You can visualize that. If I want to find n factorial, what does the recurrence say? The recurrence relation says you find n minus 1 factorial and multiply that by n, right? That's what my recurrence relation is. So whatever the number of multiplications that you encounter to find this n minus 1 factorial plus one more multiplication will give you n factorial, right? So if I want to find m of n means what? Number of multiplications to find n factorial is nothing but the number of multiplications here to find n minus 1 factorial, then plus 1. So whatever you needed to find the smaller term, which is n minus 1 factorial, then one more multiplication. And this again holds good for what? Your n greater than or equal to 1. Okay? Like the factorial itself, the recurrence relation is, this is reconciliation for what? The number of multiplications to find n factorial. Yes?
What about like fn minus 1?
It's recurrence, which means for fn minus 1 you have to go with fn minus 2. So,
but without the n or the plus 1 on the end.
Yeah, I'll tell you this. So, hold on. So the number of multiplications to find 0 factorial is what? 1. This is defined. You don't need any multiplication here, right? So this is 0. So what would you do? To find 4 that will answer your question now. So to find 5 factorial, you need to find 4 factorial times 5, right? So what are multiplication you do to find 4 factorial plus one more multiplication? But to find 4 factorial, you need 3 factorial. So that times 4. So like this, it goes all the way to 1. So you don't need any multiplication for f of 0. So the number of multiplications, so I write the number of multiplications here. The number of multiplications to find 0 factorial is 0. Right? And then one more multiplication, so it is 0 plus 1. You need one multiplication to find 1 factorial. And then this plus one more multiplication to find 2 factorial. Then one more multiplication to find 3 factorial. Then this is one more multiplication to find 4 factorial and 5. So which means to find 5 factorial you need 5 multiplications all the way from the bottom. For 0 factorial you don't need any multiplication, so it is 0. Then to find 1 factorial you just do 1 multiplication. So whatever is the number of multiplication for f of 0, which is 0, you add one more. So that's the recurrence will take care of that. Okay? So the recurrence is, because that's why it holds good for n greater than or equal to 1. And for n is 0, m of 0 is 0. Is that clear? So the same thing like I did from the bottom, 0 to 5, in general it is from 0 to n. So we'll have to show that mathematically now. Okay, so now, this is more from a common sense interpretation, but we have to basically now solve what? This recurrence relation. This should be familiar from your 225, data discrete structures. Did you solve recurrence relations there? So can you solve this? So how do you solve this? So you need the recurrence as well as the basic condition, right? So this is the basic condition. So given that m of n is m of n minus 1 plus 1, I can write it now, m of n minus 1 is m of n minus 2 plus 1, isn't it? Like, that's what it is. M of factorial of 4 is factorial of 3 times 4. So, and for that the number of multiplication is 1 more than 3 factorial. So m of n minus 1 is m of n minus 2 plus 1. So why did I wrote like that? Now I can substitute for m of n minus 1 here. What I'll substitute? This whole thing. M of n minus 1 is m of n minus 2 plus 1, right? From the recurrence. So I can now substitute this whole thing for this. And can write what? I can write m of n is m of n minus 1. I'm going to substitute m of n minus 2 plus 1. Right? So that's the term substitution for m of n minus 1. And then don't forget about this plus 1 that is out there. So that will basically be then what? Plus 1. Okay? So I'm substituting for m of n minus 1, m of n minus 2 plus 1. That's m of n minus 2 plus 1. Then this plus 1 out there. So So if you simplify this, m of n is m of n minus 2 plus 2. 1 plus 1. Okay? Right? Now just go one step further if you want. You can say what? M of n minus 2 is just m of n minus 2 from the recurrence can be written as m of n minus 3 plus 1. Right? 1 less than. So n minus 2 n minus 3 is what? N minus 3 is 1 less than n minus 2. Like this is 5, this is 4, this is 4, this is 3 and so on. So what can I do now? Instead of m of n minus 2, I can substitute this in my recurrence. Right? And I can say m of n is m of n minus 3 plus 1. Then what? Plus 2. So don't forget about the other term. So this is from for m of n minus 2, this, plus you have the 2 out there. So we have to write that 2. Okay? So what is that we have? Basically m of n is m of n minus 3 plus 3. So how far you can keep on doing that? M of n minus 3 plus 3. You can keep on doing that until you have m of 0, the basic condition. So for what value, if I substitute here, I will get 0, this term is 0. If this, it will go all the way to n, m of n minus n. Right? Isn't it? Before that, we can make it more general by telling m of n is m of n minus I plus I. Can you write like that? Because you see m of n is m of n minus 2 plus 2, n minus 1 plus 1, m of n minus 3 plus 3, and so on. So you can say m of n is m of n minus I plus I. You can say that in general. Right? So now for what value of I, if you substitute here, you can go all the way to the basic condition. If I equals n. If I say if I equals n, I can say m of n is m of n minus n plus n. Because this is how we reduce, right? M of 5, we want to find 5 multiplications. This is nothing. M of 5 is what? M of 4 plus 1, right? Then m of 4 is m of 3 plus 1. M of 3 is m of 2 plus 1. So how far you can keep doing that? Until you can find m of 0, which is 0, right? So then you back substitute, and that's what I'm doing. Okay, why? Because like you see, m of 4 is m of 3 plus 1, but if you substitute that back in this, what will you get? If you want to work out this example, you could do that. If you substitute m of 4 back into this, what will you get for m of 5? M of 3 plus 1 plus 1. This is m of 3 plus 1 for m of 4, then a plus 1 out there. Right? So that is m of 3 plus 2. Right? That is m of 5. And we can substitute this again for m of 2 plus 1 plus 2, right? So that will make it 3. Isn't it? So the same thing I'm doing here with the n minus n, n minus 1, n minus 2 and so on. The same thing. So we can go all the way up to what? Until we have m of 1 plus 4, then m of 0 plus 5. Right? So m of 0 is 0. So that's the same thing here. So you can go all the way up to your basic condition. So we went all the way to n minus n. Okay? And m of n minus n is defined as 0. So we have to go all the way to a basic condition depending on what the basic condition is. Here it is, m of 0 is 0. Okay? So since m of 0 is 0, I can say what? My m of n is simply n. Right? This is 0 plus n, so it is n, which is take off n, of course. So this n indicates what? You're doing n multiplications. To find n factorial, you're doing n multiplications. Okay? So either way, both the iterative approach of just using a simple for loop, you will do n multiplications. Using the recursion approach will also do n multiplications. So theoretically, it's the same time complexity, the same number of multiplications. But because of the overhead associated with making the recursive function calls, if you implement this, right, if you want as a practice, not as a project, though there's another different problem, but if you want to just have a feeling of it, implement the simple for loop iteration and then the recursion based implementation of factorial, run the two programs and find out which one takes more time. The recursion will definitely take more time. Okay? Not because of the actual algorithm, but because of the overhead in calling the functions, recursive functions. Okay? Alright, any question on this? So you should be very familiar in solving recurrence relations. We'll do some more examples, but practice if you're not comfortable with solving recurrence relations.
That's right.
Yes.
So at the m is 0, you say is set to 0 or set to 1?
That's big, in this case m of 0 is 0 because to find 0 factorial we don't need any multiplication. 0 factorial is 1, that's well defined.
Okay.
Right? So you don't need any multiplication to find 0 factorial. So what m of something means? M of n means number of multiplications here to find n factorial. So m of 0 means the number of multiplications here to find 0 factorial because no multiplications needed. That's why it is 0.
Okay.
Okay? Alright, so let's do the next problem. This also we did in the first class. If you remember, I wrote that thing there. Let's say we'll come back to that. So what we want to find is, we want to find the number of bits in the binary representation of an integer. Okay, so for example, if I take up an integer, say 10, how many bits are there if I represent it in binary? I don't want the actual binary form, but I want to find the number of bits that are out there. Okay? So first of all, what is 10 in binary? 10 in binary is this, 10, 10. Right? So, why? Because if you have the exponents of 2, did I tell you that? Sometime back I told you this. Exponents of 2, 1, 2, 4, 8 and so on. So wherever there's a 1, add the corresponding exponent of 2. So 8 plus 2 is 10. Right? That's how you can interpret this as a binary representation of 10. So how many bits are here? How many bits are here? 4. So this is the answer we want in this case. So the number of bits in the binary representation of 10 is 4. So in general, if there are integer n, how many bits are there in its binary representation? You see what problem we are trying to solve? Given an integer n, you want to find how many bits are there in its binary representation. Okay? Clear? If you have something like 30, how many bits are there? Anyone say? 30 is what? 16, 8, 4, 2, 0. This is 30. So there are 5 bits in a binary representation of 30. Okay? So this is what we want. The final answer is 5. The number of bits in the binary representation is 5. Here it is 4 and so on. So let's try to do this. Start from integer 1. In integer 1, how many bits you need to represent integer 1? 1 bit, just 1 itself, right? So you have 1 bit to represent 1. If you want to represent by 2 in binary, how many bits you need? 2 bits. For 3, 2 bits. 1, 1 is 3. 4 is 1, 0, 0, so you need 3 bits. Then 5 is 1, 0, 1, 3 bits. 6 is 1, 1, 0. 7 is 1, 1, 1. I hope you understand what I'm talking, right? Binary. So from 4 to 7, you need 3 bits. 4 is 1, 0, 0. Then 5 is 1, 0, 1, 1, 1, 0, 1, 1, 1. So this is 4, this is 5, this is 6, this is 7. So you need 3 bits in for each of them. So from 4 to 7, you need 3 bits. Then likewise, from 8 to what? 15. Because 8 is 1, 0, 0. 16 to 31, you need 5 bits. And then from 32 to 63, you need 6 bits. Anyone can say what's the next range? I have not written here. Can anyone tell?
64 to 127.
Good. 64 to 127. How many bits you need?
7.
7 bits. And then can you say the next range?
128, 255.
255, you need 8 bits. Good. So you see the range actually doubles. 2 to 3, and then 4 to 7. Then you see the number of integers covered here is 2, right? 2 and 3, 2 integers. Then 4 to 7, how many integers are there? 4 integers, 4, 5, 6, 7. Then 8 to 15, 8 integers are there, 8, 9, 10 up to 15. Then from 16 to 31, you have 16 integers, 16, 17, 18 up to 31. Right? So you double the, as you increase the number of bits, the number of integers you can cover doubles. Right? That's what's binary basically. If you move towards the left, as you add each bit towards the left, you can cover twice the range. Is that clear? Okay? So, what we want to find, given some arbitrary integers, 1,000 or something, right? For any given integer, if I want to find the number of bits needed, let's pick up something in what we have written itself here. Let's say we want to find for 40. If I want to find the number of bits needed to represent 40, what will you do? What will you do? Look at this, right, and find what range it is. It is actually in this range, right? Okay? So it is 6 bits. But this is if you want to look up like this, but if you want to find algorithmically how many bits do you need to find for any general integer, what will you do? You need a recursion. So which means whatever the number of bits are needed for the particular, you see here, to find the number of bits needed for 32, it is 1 more than the number of bits needed for the previous range. So half of 32 is 16, right? Half of 33 is kind of 16.5, but if you kind of truncate the fractional part, it's also 16. Then 34, half of it is 17. 35, half of it is 13.5, but still it is 17. So on you can go up to 62 and 63. 62, half of it is 31. 63, half of that is 31. So I can come up with this general recurrence. The number of bits needed to find for n is what? The number of bits needed to find n over 2 with the floor plus 1. Why that floor? Because as I said, if you want to find the number of bits needed for 33, right? It's basically the number of bits needed to find what? 33 over 2 with the floor plus 1. So whatever the number of bits needed to find, 33 over 2 is 16.5. And if you take a floor means what? You're removing the fractional part. So the number of bits needed to find 16. Whatever is the number of bits needed for that integer 16 plus 1 more bit. That's what this shows you. So because whatever is needed for 16, which is 5 bits, plus 1 more bit is needed for the next range. So 33 falls in the next range, right? Compared to this. Do you see what I mean? So whatever is needed for the previous range plus 1 more bit. Is that clear? So likewise, how many bits you need for 16? Whatever is needed for the previous range, in this case 16 over 2 is 8. So whatever is needed for 8 plus 1. Right? To find 8 you need 4 bits. To find the number of bits for 16 you need 1 more bit, 5 bits. Right? This increases by 1 for every range. Is that clear? So to find number of bits needed for an integer, basically you have to find number of bits needed for half of its value, truncated, which means removing the fractional part. Whatever is needed for half of its value plus 1 more bit is needed for this integer. And for that particular half this value, you don't need to know this right away. Just do the recursion like we did for factorial. If you need to find for 33, find for 16. Then for 16 you find 8. Then for 8 you find 4, 2. And this is the basic condition. For 1, the number of bits needed is 1. And then you go back. If you want to find 1, you need 1 bit. If you want to find, you need 2 bits. Then 4, 3 bits. 8, 16, 4 bits and so on. Same thing now for 40. Let's now do for 40. To find the number of bits needed for 40, you need the number of bits for 20. Right? Plus 1 more bit. And then to find for 20, you need the number of bits needed for 10. Plus 1 more bit. And then to find the number of bits for 10, you need the number of bits for 5. Plus 1 more bit. To find the number of bits for 5, you need the number of bits for 5 over 2 is 2.5. But you are going to truncate because of this floor here. Right? The number of bits needed for 2 plus 1 more bit. Then number of bits for 2 is half of it is 1. So number of bits needed for 1 plus 1 more bit. But you know in the basic condition, number of bits needed for 1 is what? 1 bit. So now add up from the bottom. So the number of bits needed for 1 is 1 bit. Then for 2 you need 1 more than the previous case. So this is 2 bits totally. Then for 5 you need 1 more than the previous 3 bits. For 10 you need 1 more than the previous 4 bits. For 20 you need 1 more than the previous 5 bit. For 40 then 1 more than the previous 6 bit. And you see that 40 falls within this range. You see now how everything comes together? Yeah? So the recurrence relation is number of bits needed for n is number of bits needed for n over 2, the floor plus 1. Any question? Yes.
Why are we using the floor function versus the
Because
ceiling?
as the range doubles, right? If you're going from the higher one to the lower one, you need to do that. You see, from 8 to 15, then you go to 16 to 31, right? So if you want to use this recurrence, the number of bits needed for 16 is, number of bits needed for half of it is 8 plus 1 more bit, right? For 17, half of it is actually what? 8.5. But we are working with integers here. And the number of bits needed for 8 and 8.5 doesn't really make sense because they are all integers. So you have to truncate to the nearest, to the integer 8. You have to remove the fractional part.
Also, with the floor, you're moving down, the ceiling, you're moving up.
Yes, floor means truncating basically. So if you have 8.5, the floor of it is 8. So removing the fractional part.
Okay.
Floor always think, you see that lower thing here. So remove floor means to the bottom. Seal is actually like this, or to the top. So 8.5 is 9. So moving to a higher integer. Floor means you're moving to the lower integer. Okay?
Okay.
So we have now established a recurrence to find the number of bits for finding for any integer n. And that's what is this pseudocode. If you want to find the number of bits in a binary representation of an integer n, if n is 1, of course, number of bits needed is 1. That's your basic condition. So you return 1. Otherwise, you keep calling it back. So to find the number of bits for n, as I wrote here, it is the number of bits for n over 2, the floor, plus 1. And you keep calling it back like as we did, all the way as until you get n is 1. Once you get n is 1, the function will return 1, which means 1 bit is needed. And then you go back to the next recursive call, so 1 more than the previous, so 2 bits, then the next recursion call, 1 more than this, and so on until you get back to that integer. So again, it's an overhead because you have to store all those function calls in memory. Okay? Is that clear? So that's how you find this thing, number of bits needed to represent an integer. Now, we want to analyze the time complexity, right? So, can you say